Okay, we're back. You guys are up to the time here.
Okay. Oh, thanks everyone for doing this.
Thanks for inviting me.
Yeah. Well, you know, I think we have a really good lineup today, so excited for all you folks.
I think this was one of the first like seminars that I watched when I started my PhD like a year ago.
Oh wow.
It's
Oh, that's
kind
great.
of funny. Yeah, Tim Merlis was presenting then about high clouds also.
I think it's really funny because I don't know if this would have existed except for the pandemic.
Yeah.
Andy and Christy thinking that there should be something like this, but I don't know. I volunteered because I'm so glad this thing exists. Hopefully we can keep it going. Maybe I'll put up the welcome slides. This is very funny. Peter seems to be. Sorry about that. My computer seems to have crashed or something like this. My keyboard stopped working, so that was entertaining. Perfect timing for that. Let's see.
No,
Just give it a minute for people coming in. Okay, I'm gonna give this a start. Also, someone out there I think has their mic on and might be enjoying lunch or something like that. So if you're out there and that's the case, maybe there we go. Okay. or maybe dinner. I don't, breakfast, all options are possible on a Zoom. Hi, everyone. Welcome to a Northern Hemisphere summer edition of the ECS and Cloud Feedback Virtual Symposium. This is our 35th event, which is pretty great that we're going along. And we have a fantastic collection of speakers today. A lot of interesting research to share with you. We have 3 talks, and each of them is going to be about 12 minutes. We're going to give a 2-minute warning before the end of the talk. There'll be some times for questions at the end of the talk, and then if there's some time at the very end, we'll have a more general Q&A with some discussion. Now, if you have a question, you can type them at any point into the chat. You can also raise your hand using the Zoom option to do that, and then we'll unmute you and you can ask a question. I think you might be able to unmute yourself to do that, but anyway, you'll be able to ask your question. If you would like to give a talk, we're always looking for more people to speak. You can reach out to any of our committee members, our organizers. And you can find our contact information at this website, as well as videos of all of our past sessions, the sign up for the mailing list, and a lot more. So that's kind of the logistics. Oh, someone say something? Okay. But in any case, our first speaker today is Jakob Deutloff, who's a PhD student at Max Planck Institute, and he's going to be talking about the high cloud radiative effect. So, Jakob, why don't you go ahead and share your screen, and we can get started.
Yeah, thanks a lot for the introduction. I hope you can see the right screen.
Looks good.
Looks good. Okay, great. And yeah, thanks also for the invitation. It's really cool to be here. So yeah, I'm going to show work that I did in the first year of my PhD, and it's about how we can understand the tropical high cloud radiative effect better by looking at it as a function of the ice-water path. And yeah, this picture already kind of shows what the talk's going to be about. So you have this big anvil cloud shield here that kind of covers all the low clouds and the ocean below it, and we want to try to understand its radiative effect a bit better. And yeah, the motivation for this is pretty simple. So as you probably all know, the high clouds cause a lot of uncertainty in climate sensitivity. And this is nicely shown by this Sherwood et al. Study who partitioned the cloud feedback. And you see that the 2 components that correspond to the anvil clouds or to the high clouds are the cloud area feedback and the cloud altitude feedback here. And yeah, as you can see, especially this area feedback is associated with a lot of uncertainty. We want to work towards reducing that. And the idea that we have for this is to really interpret the high cloud radiative effect as a function of the ice-water path. And this plot kind of shows how this idea works out. So up here, you see the cloud fraction just as a function of the ice-water path. And you see the very thin clouds at the low ice-water path are these kind of high cirrus. Then you go towards your more anvil clouds, and then towards your deep convection at the very high ice-water path that reach throughout the whole column. And then down here, you see the cloud radiative effect, also as a function of ice-water path, and you see the very thin clouds, they don't have an effect. And then when you go to the thicker clouds here, but still pretty thin, the long wave cloud radiative effect is kind of stronger than the short wave, so they have a net warming effect. And this balance shifts here at around 10 to the minus 1 kilograms per meter square to a net cooling effect. And yeah, this idea is not entirely new, but was developed by Barry et al., among others, based on satellite measurements, and was then recently applied also by Sokol et al. To high-resolution RCE models. And our idea is now really to try to understand what sets this relationship of the high cloud radiative effect as a function of ice-water path. And the data that we use for this, which is also what I show here, are radiative flux transfer calculations with the ARTS radiation model, which are based on Icon atmospheric profiles. So atmospheric profiles from an icon simulation with 5-kilometer resolution and in an unforced state. And yeah, so how we want to achieve this goal. So this is, that's what this slide is about. So we develop a conceptual model to really try to break down the complexity of the high cloud radiative effect as much as possible. And within this conceptual model, we approximate the high clouds just as a single layer with, again, this idea of having thin clouds and going towards thick clouds based on the ice-water path. And then anything below the high clouds is just referred to as the lower troposphere. And yeah, we have a shortwave and a longwave component. And for the shortwave component, we assume that there is some incoming solar radiation, which then hits the high cloud. And based on the albedo of the high cloud, part of this radiation will be going through the high cloud and hit the lower troposphere, which is also characterized by an albedo. And this albedo has a contribution from low clouds based on some low cloud fraction and a contribution from clear sky regions. And yeah, this radiation that goes through will be reflected and then experience multiple reflections between these two layers. And in the end, we will have some radiation that is reflected by the Earth in total. So we have one part here directly from the high clouds, and then this more complicated term, which also includes these multiple reflections. And for the long wave component, we assume that the lower troposphere will emit some upwelling long wave radiation, which is again constituted by a contribution from the low clouds here and a contribution from clear sky regions. And then we also introduce a correction factor here that accounts for the moistening of the columns when we go from low ice water path to higher ice water path. And yeah, this upwelling long wave radiation will then hit the high cloud, and based on the emissivity of the high cloud, part of it will go through the high cloud. And of course, the cloud also emits radiation based on its emissivity and temperature. So this is kind of the whole picture. And we can use this conceptual model now as a tool to understand the ingredients of the high cloud radiative effect by parameterizing it with the ARTS radiation data that we have. And we do this first for the high cloud. So we start with the high cloud temperature, which we can diagnose from the ARTS data. And we see that the very thin clouds are characterized by pretty cold temperatures, so they are high up, whereas then the anvil clouds are a bit lower and warmer. And when we go to the very thick clouds, we see that they are again characterized by colder cloud top temperatures. And based on this temperature, we can then also diagnose the emissivity of the clouds. We see the thin clouds are really transparent to long wave emissivity. Then we have this transition in between, and the thick clouds are opaque. And the albedo kind of looks similar, but it saturates at values around 0.8. So this is all we have for the high clouds. And then for the lower troposphere, we start with the low cloud fraction. And if we just plot this as a function of the ice-water path, we see it's relatively constant. So we just approximate it to be a constant. And with this low cloud fraction, we can then understand the lower troposphere albedo. So if we just plot the different data dots, we see there's a lot of contributions from low clouds here with these blue dots, which are the high values. And we have some contributions from clear sky regions, which are the black dots. And then we calculate the constant value for the low clouds and for the clear sky regions, and mix the two based on the low cloud fraction, which is then this red line here, which goes into the model. And we see kind of the same for the upwelling long wave radiation. So we have some data that comes from the low clouds, which is less upwelling long wave radiation. And then we have the clear sky values. And you can already see this kind of linear drift that we have here, which is due to the moistening of the columns with higher ice water path. And this is what we approximate with this correction factor, which then basically gives you the slope of this line. All right, so this is all the input that we have for our conceptual model. And the question now is this enough to explain the shape of the high cloud radiative effect that the ART simulations predict? And actually it fits quite well. So the art simulations are the dotted lines, and the solid lines is the conceptual model. And as you can see, they agree quite well. So that makes us happy. And it makes us happy because now we can understand really what controls the high cloud radiative effect as a function of ice-water path. And for the long wave component, we see that for the thin clouds, the increase in the long wave cloud radiative effect is really governed by the increase in emissivity here. Whereas for the thick clouds, where the emissivity reaches 1, we really need the high cloud temperature to explain the continued increase. So this is linked to the cooling of the cloud tops with the higher ice-water path here. And for the shortwave part, it's a bit more easy to understand. So it's really just the albedo, the increase in the high cloud albedo that explains the increase in the shortwave cloud radiative effect. And yeah, now the next step that we can do is to try to recover the total high cloud radiative effect of all high clouds. And for this, we need to know the cloud radiative effect or the radiative effect of the individual cloud, and then also how frequently it occurs, which is this ice-water path histogram here. And you can see the thin clouds are more frequent than the thick ones. And if you take the two and multiply them, you really see the individual contribution of the various clouds. And the area under the curve here is now the total cloud radiative effect. So if you just sum across this whole thing, you get these numbers here, and you see for the arts values, we see shortwave and longwave are kind of canceling out to a weak positive net value. And this is really well matched by the conceptual model as well. And yeah, this means that we can also use this conceptual model as a tool to look at high cloud feedbacks in kilometer scale simulations, and then understand really from which region the feedback comes from, and maybe look at these known mechanisms like the proportionally higher end temperature hypothesis, and stuff like this in this new ice-water path perspective, which is what we plan to do next. And yeah, this brings me to my conclusion. So we developed this conceptual model of the high cloud radiative effect that really tries to break down the complexity as much as possible. And this actually produces a very similar high cloud radiative effect as the art simulations. So it allows us to understand really what governs this relationship of the high cloud radiative effect and ice-water path. And for the shortwave component, it's really just this increase of albedo. And for the longwave component, we have to separate the thin clouds and the thick ones. And for the thin clouds, we see that the increase in emissivity governs the increase in the longwave cloud radiative effect. And then for the thick clouds, it's really the decrease of cloud top temperature with ice-water path. And yeah, that's it. Thank you.
Great, perfect on time. Thanks, Jakob. Yeah, we have a few more minutes for questions. So if anyone wants to jump in and ask a question, then just unmute yourself. Lazarus, do you want to ask a question?
Yeah, very simple question, actually. What happens to shortwave cloud absorption seems to be neglected in the schematic you have there for your conceptual model.
Yeah, that's true. That's neglected, like other things. And yeah, kind of that we can still match this cloud radiative effect kind of shows that maybe it's not so important. So for example, we also neglect any emissions above the high clouds that the atmosphere could have, like stratosphere or anything like this. But yeah, also shortwave absorption of the clouds is something we neglect.
So is this cloud radiative effect global, tropical and extratropical atmospheres then?
No, sorry, that's just tropics. Maybe I should have said this more clearly.
Okay, so I suspect that, for the thin ice clouds, there's not much shortwave absorption. And for the thicker clouds, I think the total column absorption of the clear and cloudy atmosphere is about the same, probably, because you're cutting off solar from the large troposphere where it's humid and it would be absorbed. So probably that explains why this works even if you neglect the shortwave absorption for the thicker clouds. It's a little bit surprising, but I think the total column is probably conserved. That's why you get that result.
Cool. And then Jonah, and then Keith.
Yeah, hi. Yeah, very nice talk. Thank you very much. I noticed that your dots, which I guess come from the art scheme for the long wave emissivity, many of them are greater than 1. Is there an obvious reason why that is?
Yeah. I get this question very often. But yeah, that's basically because our approximation is not always perfect. And sometimes like we derive this emissivity based on the assumptions that we make here in the conceptual model. And sometimes if these assumptions are not perfect, we might get an emissivity that's higher than 1. So yeah, this is basically shows imperfections in our conceptualization. But in the mean, it's more or less limited to 1.
Okay, thank you.
Cool. Maybe so we can keep on time and have a bit more space for discussion at the end. Let's move on. But thanks again, Jakob.
Yeah, thanks.
Thanks again. That was a great talk. Our next speaker is Paulina Czarnecki, who's a PhD student at Columbia, and she'll be talking today about the radiative forcing of optically thin gases. So Paulina, maybe if you want to have your slides. Excellent. And take it away.
Great. Yeah, thank you for the introduction. My name is Paulina Czarnecki. I'm a 5th-year PhD student at Columbia working with Robert Pincus and Lorenzo Polvani. And I'll talk about some recent work that we've been doing. So there's been some recent work by Nader Jivanji, among others, to develop a simple analytical model of radiative forcing by carbon dioxide, and I'll briefly introduce this model. In this work, they assume that each wave number in the CO2 band emits or contributes to the outgoing long wave radiation at a given emission pressure. And that emission pressure is where optical thickness is about 1. And with the help of some idealized spectroscopy, they can draw these emission pressure triangles between the 2 states. So the solid line is for a lower concentration of CO2, and the dashed line is a higher concentration of CO2. And then this allows them to make a geometric argument for the forcing, where if you subtract the area of these 2 triangles, you get new emission in the stratosphere in this green, blocked surface emission, where wave numbers that were optically thin are becoming optically thick in the wings of the band, and all the yellow stuff cancels out. So this allows them to write a really neat equation where L comes from the spectroscopy. The log Q is the logarithmic change in concentration between the 2 states. And then you really boil down to the difference between surface and stratospheric Planck emission. I'd like to highlight that this equation really shows this well-known log dependency of CO2 on concentration, which is of CO2 forcing on concentration, which is a phenomenon that has been studied by others as well. Here's a figure from David Broms's paper. And this emission pressure idea really hinges on the assumption that gas emits entirely where optical thickness is 1. So this won't apply to other gases. For example, the ozone depleting substances, the CFCs included in that, exert a forcing that is about 1/3 of CO2 forcing, as shown in this figure from Lorenzo's paper. But CFCs are not optically thick anywhere in their band, so this really neat model, unfortunately, won't work in that case. So here we'd like to use a very similar approach to understand forcing also by optically thin gases. I'm going to very briefly go through the derivation. This is just the monochromatic definition of forcing. So the difference in outgoing long wave radiation between two states, in this case, pre-industrial and present day, concentrations of CFC-12. And here I'm just plugging in the Schwarzschild's equations, the physics of the outgoing long wave radiation at the top of the atmosphere. If you're familiar, all of these symbols have their usual meanings. The curly T is transmissivity, or e to the negative tau, where tau is optical depth. B is the Planck function. And I'm just going to combine like terms, define delta curly T as the change in transmissivity between these two states, the pre-industrial and present day. This is just the equation from the previous slide that I have rewritten, and I'm going to make my first assumption. So I'm going to assume that we can just take the average of the Planck function and pressure through the atmosphere and pull it out of the integral. I'm not going to do the math here, but this is equivalent to saying that delta T is linear in pressure. And here's a little plot to justify that. I'm just plotting delta T for various prescribed values of optical thickness. And you can see this black line is for a very optically thin gas, and delta T is indeed linear in pressure. Then we can just solve this integral directly because it's the integral of a derivative. Plug in the bounds, and we're left with this equation. I'm going to make one more assumption, which again requires tau to be very small. I can Taylor series expand this exponent and replace delta transmissivity with delta optical depth. So then we have a complete monochromatic model where this is surface black body emission. It's attenuated by the mean atmospheric absorption and scaled by the change in optical thickness of the atmosphere due to the perturbation concentration. So we've made no assumptions on spectroscopy. We've only made assumptions on optical thickness. So we can see how this model works monochromatically. I can just plug in optical thickness values from my line by line model, where I'm just importing a bunch of spectroscopic data, calculating the exact radiation, or as close to exact as we can get. And I'm plotting the line by line, the reference calculation in the solid lines and the model in the dashed lines for 3 different gases, CFC-12, CFC-11, and optically thin CO2, where I have just imposed a very small concentration for CO2. And you can see that they track each other quite well. So the theory works monochromatically. But of course, we're interested in the total value of the forcing, so we have to integrate spectrally. This is the absorption coefficient of CFC-12, and you can imagine integrating across this is difficult. So we'll have to make some more approximations. This is just the equation for optical thickness at a given pressure. And it's just some constants. D is the two-stream coefficient, Q is the concentration, G is gravity, multiplied by the absorption coefficient. We're going to follow mostly Nader-Givenchy's work, but also others, and assume that the absorption coefficient doesn't vary much in pressure. And you can see that if I want to integrate this spectrally, really the only thing that varies here is the absorption coefficient. And our model is linear in this quantity, so it's linear in absorption coefficient. And we can take advantage of the mean value theorem, which tells us that the shape of the spectrum doesn't really matter. We can replace the absorption coefficient with a box of equivalent area, shown by this line. So plug that all back in. We have our Planck term, which is unchanged from our previous model, except that we're evaluating at the central wave number, again, following some others' work. This is the band mean atmospheric thickening, delta tau, dependent on the change in concentration. K-ref is our the height of this rectangle that I drew. And then, of course, you have to multiply by the width, which is the width of the band. So in order to kind of demonstrate that the model will work across Earth-like conditions, I'm going to show a map of model and line-by-line forcing for some conditions taken from AREP 5. This is CFC-12 only, so there's no overlap by any other gases. There's no other gases in this atmosphere. The model is on the left, and the line-by-line reference calculation is on the right. And I'm also plotting the zonal mean. And you can see they track each other quite well. We have also addressed overlap with water vapor. I won't get into it. We're largely, again, following Nader Givenchy's work, where you can assume that wherever water vapor is optically thick, you just raise the surface to that level. You replace the surface with where water vapor is emitting. So again, they track each other quite nicely. You can see some attenuation by water vapor where there's a lot of moisture, but you can still see the total forcing even when water vapor is optically thick. So now we want to see what insights we can draw from this model. We're interested in the shape of the forcing with concentration. So again, there's this well-studied idea that CO2 forcing increases logarithmically with concentration. From our model, everything's linear, so we expect the change in concentration to have a linear change in forcing. And indeed, this is just line-by-line forcing for the 3 optically thin gases, CFC-12, CFC-11, and very small concentrations of CO2. And I've just fit a line to it, and you can see that the behavior looks pretty linear. There's other gases that don't really exhibit linear or logarithmic behavior quite as neatly. N2O is a really interesting example because it has multiple bands that contribute to the forcing. So here I'm plotting the optical depth at the surface for some intermediate concentration of N2O. And you can see that there's...
warning. Right.
Oh, thank you. There's 2 bands that are optically thin, smaller than this tau equals 1 line, and 1 band that's optically thick. And you can imagine that as I change concentrations, this might cross the tau equals 1 line. So we expect that the optically thin bands will give us a linear shape with concentration, and the optically thick bands will give us a logarithmic contribution. So again, this is just line-by-line calculations of N2O. I've split it across these 3 bands. The light colors are where the band is optically thin, and the darker colors are where it's optically thick. And I've just fit either lines or logs respectively. And you can see that these fits work quite well. And so we can conclude that the total shape of the N2O forcing will be some sum of logs and lines. Finally, one of the nice things about a simple model is that we can turn the knobs and see what happens, draw some understanding. So we want to ask what controls the magnitude of forcing by a given gas. And there's 4 ways that it can vary. So the Planck function varies across the spectrum. For example, CO2 is around here, and CFC-12 is out here further. The absorption coefficient, or the cross section, in our case, this is a linear relationship, but CFC-12 has a much larger absorption coefficient on average than CO2. The concentration, CO2 is a lot more abundant in our atmosphere than CFC-12. And the bandwidth, I'm going to ignore that because CO2 and CFC-12 have very similar bandwidths, and so for the sake of this comparison, I will skip it. So I'm just showing here a single column of CFC-12 forcing and CO2 forcing where I've changed the CO2 concentration to be equivalent to the CFC-12 concentration. So it's optically thin. The diamonds are the line-by-line reference calculations, and the circles are the model that I fit for this particular gas. If I move CFC-12 to be centered at the CO2 band, here's a little schematic to illustrate that. You get a modest increase in CFC-12 forcing. if I change the CFC12 absorption coefficient to CO2s, you get a more dramatic decrease in the forcing. And of course, if I do all of these things, I can move from the pink to the yellow. That's all variables. So we can conclude or demonstrate that CFC12 is a more powerful forcer per molecule than CO2, largely because of its bigger absorption cross-section. So I will just leave this here because I think I'm out of time. But thank you for having me, and I'm happy to answer questions or over email.
Awesome. Thank you, Paulina. Great talk. Yeah, again, we have a couple of minutes for questions. Okay, that was a comment. I think that was a comment from Rob Wood on Jonah's question. Nather, do you want to unmute yourself?
Sure. Hi, Paulina. Great talk.
Hi, thanks.
Yeah, and awesome to see this approach taken for the optically-thin gases and to explain this linearity. It goes back a long way. And in fact, my impression from some of the literature is that people explain some of these different shapes of the forcing curves, linear, log, or even square root, in terms of individual line properties, which I never felt comfortable with. And I think this kind of shows that maybe it is in fact different physics and spectral line properties that gives these shapes to the forcing curves. And in particular, for some gases, I forget which, maybe N2A, maybe also methane. Some of the fits that are used in the IPCC process, have square roots in them. But you had a nice figure showing that you could just take a linear regime and match it to a log regime. So is the square root, was that just a fit to what really is linear morphing to log?
Yeah, can you still see my screen?
Yes.
I have a bonus slide, because I thought I might
get that question.
Yeah, so I was reading about this last week in preparation for this, and like you said, the square root seems to come from the strong line absorption limit, which again isn't quite the way that you and David Romps and others and Pierre Humbert and others explain the logarithmic shape of CO2. And here I am plotting that same figure that I showed before for N2O, and I've created my own square root fit to that shape, and it doesn't seem to fit as neatly as the log or the line fits, although of course, I mean, I'm not a spectroscopist, so I'm not ruling out that there could be line shape or absorption limits at play as well. I haven't gotten into proving that in any sort of rigorous way.
Right. But this figure is nice because it suggests that in addition to a transition from linear to log, that you're also summing over bands.
Yeah.
And so when you kind of add all that together, that there's multiple bands, each with their own transition from linear to log, then you end up with something that you might try and fit by a square root, but then that's actually pretty empirical then.
That's my theory. Yeah.
Okay. Maybe I'm being a bit more bold in saying that.
I don't know if I've done it carefully enough to be super firm about it, but that would be my guess. Yeah.
Gotcha. Terrific. Thank you.
Thank you.
All right, fantastic. I think we should thank Paulina again and move on to our next talk. It was great.
Yeah.
Thank you, Paulina. That was great. Our final speaker today is Joonsuk Kang. He's a PhD student at UChicago, and he's going to be talking about SST trend discrepancies and how it might impact some of our understanding of extratropical circulation trends. Joonsuk, oh, great. Take it away.
Yeah, you can all see my screen, right?
Yes.
Okay. Hi, I am Joonsuk. I'm a fifth-year PhD student in University of Chicago, and like to thank the organizers for having me, and I'll be talking about a slightly different thing, which is about how sea surface temperature trend discrepancy impact the circulation trends in the Southern Hemisphere. And I'll be talking mostly about the Southern Hemisphere storm tracks, which is the wavy circulation patterns we see in the picture down there. So this is work done with my advisor, Tiffany, and also with Sarah, Isla, and Hewitt. So as you could see, this figure we've seen many times, there is this difference between the temperature trends in the observations and the Symposium models. And the observed SST trends are characterized by a La Nina-like temperature trends in the tropical Pacific and a Southern Ocean cooling in the Southern Ocean. And this is not well represented in the Symposium models. And over the last couple of years, we've learned how this different sea surface temperature pattern impacts the climate sensitivity and the regional and the global energy budgets. And in that perspective, it's reasonable to think that it could also impact the circulation trends in the extratropics. However, it is currently unclear how the circulation trends are impacted by these different SST trend patterns. And this is particularly interesting question because our latest generation of coupled climate models, which does not capture the sea surface temperature trends, are underestimating the circulation trends in the Southern Hemisphere. So the figure here shows the time series of Southern Hemisphere winter storm tracks in reanalysis in blue and Symposium models in black. We can see that in reanalysis, the Southern Hemisphere circulation is strengthening, and the Symposium models fail to capture the rate of the strengthening over the historical period, and similar intensification occurs by the end of the 21st century. So this leads to us a question whether this underestimation of the circulation strengthening has anything to do with their misrepresentation of sea surface temperature trends. So, but how can sea surface temperature trend affect the circulations? So we can learn from interannual variability comparing La Nina and El Nino years. When during La Nina winters, there is a Rossby wave teleconnection from the equatorial Pacific to the South Pacific, characterized by a weaker subtropical jet and stronger mid-latitude jets as exemplified in the figure here. So this pattern of Rossby wave teleconnection favors stronger storm tracks in the South Pacific. Also, the Southern Ocean cooling can impact the circulation trends by changing the atmospheric energy gradient. And if we think about Southern Ocean cooling as equatorward energy transport in the oceans, it would impose stronger energy gradient, equator to pole energy gradient in the atmosphere, which could strengthen the extratropical circulation. And the figure here shows that there is some difference between the surface energy flux trends between Era 5 and Symposium models, which reflects the difference in ocean heat storage and transport trends. So in this talk, I'll try to answer these two questions. So first, are sea surface temperature trend discrepancies in the tropical Pacific and Southern Ocean important for the Southern Hemisphere winter circulation trends? And also second, how does different SST trend discrepancies impact the circulation trends? I'll start answering this question by first looking at the trends in circulations in reanalysis. So the figure here shows the trends in reanalysis circulation, especially I'm looking at the wintertime storm track trends. And we can see that there is a large spread in reanalysis trends. And however, most of the reanalysis, and especially the newer ones indicated by darker colors, show strengthening trend. And when we compare these trends of strengthening circulation to those in the Symposium models, we find that the Symposium models have weaker trend than most of the reanalysis. So although there is a large spread in reanalysis trends, we can say that the Symposium models are likely underestimating the strengthening circulation in the Southern Hemisphere. However, when we compare these trends with the prescribed sea surface temperature AMIP simulations, we see that the trends are significantly larger. When we compare the trends distributions between the AMIP 6 and the Symposium CMF6 models using a t-test or similar non-parametric test, we see a statistically significant difference that the AMF6 models are producing stronger trends than the coupled simulations. We can better understand this difference by looking at the spatial pattern of the circulation trends. So the figure here I'm showing is the storm track trends in the reanalysis and also the CMF6 and the AMF6 models. And as we can see first in the reanalysis, we see a strengthening trend across all longitudes. However, in the CMF6 models, we see a overall weaker trend and especially near zero ensemble mean trends in the South Pacific. And this is different from the AMF6 models, which has prescribed SSTs and captures the trend. We see a stronger trend, especially in the South Pacific. So if we create a similar plot as the previous one, and just for the South Pacific, we see a stark contrast between the CMF6 and AMF6 models in their circulation trends. So this makes us think that SST trend discrepancy in the coupled models could be contributing to the underestimation of their circulation trends. So we test this idea by using the CSM2 pacemaker simulations. The pacemaker simulations are fully coupled simulations, except in the targeted region where the SST is nudged to the observations. So by taking the difference between the free-running coupled CSM2 large ensemble simulations and the pacemaker simulations, you can quantify the impact of the regional sea surface temperature trend discrepancy on the circulation trends. So we'll start by looking at the impact of tropical Pacific sea surface temperature trend discrepancy by using the Pacific pacemaker simulations. In the Pacific pacemaker simulations, the sea surface temperature in the equatorial Pacific is nudged to observations, and therefore it captures the sea surface temperature trends in the tropical Pacific, as we can see in the figure here. And so when the coupled simulations captures the sea surface temperature trend in the tropical Pacific, we see that there is a strong intensification of circulation trends in the South Pacific. So the figure here I'm showing is the storm track trends in the coupled CSM2 large ensemble simulations in the top and the Pacific pacemakers in the bottom. And when we compare these two panels, we can see that there is a large intensification of the storm tracks in the South Pacific. And this is possible because the pacemaker simulations captures the La Nina-like teleconnection trends from the equatorial Pacific to the South Pacific. The figure here I'm showing is the 250 hectopascal zonal wind in colors and anti-geopotential height trends in contours. We can see in pacemakers and reanalysis, there is a weakening of the subtropical jet indicated by the blue colors here and the strengthening of the mid-latitude jet indicated in the red colors here. So this favors the storm tracks to strengthen in the South Pacific. In contrast, in the coupled CSM2 large ensemble simulations, which almost produces an opposite El Niño-like warming trend, they show an opposite wind trend, which is unfavorable for this circulation to strengthen in the mid-latitudes. How about regions other than the South Pacific? To examine this issue, we investigated the impact of Southern Ocean cooling trends on the circulation trends by using the Southern Ocean pacemaker simulations. And just like the Pacific pacemakers, so Southern Ocean pacemaker simulations nudge the sea surface temperature to the observations in the Southern Ocean, therefore captures the Southern Ocean cooling trends, as we see in the figure here. And when the coupled simulations captures the Southern Ocean cooling, it shows an overall intensification of the circulation trends in the Southern Hemisphere. So again, we are seeing similar figure as before, but in this case, the bottom shows the storm track trends in the Southern Ocean pacemakers. And when we compare this to the coupled free-running CSM2 large ensemble simulations, we can see that there is overall strengthening across all longitudes and especially at the higher latitudes. And this is possible because the Southern Ocean pacemaker simulations improve the ocean heat transport trends in this couple CSM2 large ensemble simulations. So the figure here I'm showing is the ocean heat transport trend inferred from surface energy fluxes. And we can see that in the Southern Ocean pacemaker simulations in era 5, there is an equatorward energy flux trend. And which is in contrast to the couple CSM2 simulation, which shows the poleward energy flux trends in the ocean. So when the ocean transports heat more equatorward, it imposes a larger energy gradient in the hemisphere. Therefore, it strengthens the poleward energy transport in the hemisphere, and therefore it strengthens the storm tracks. And as a final piece, we can think about combining the impacts of these two pacemakers together. And we do this by adding the ensemble mean impacts of individual pacemakers to the CSM2 large ensembles and creating a synthetic large ensemble. And in this synthetic large ensemble, which we name SUM,
Sorry, 2 minutes.
and the trends of the storm tracks are as close to that simulated by the prescribed SST simulations. So when we compare the figures on the bottom and the top and bottom, we can see that the strengthening and the pattern of the strengthening is very similar. So this confirms us that the sea surface temperature trend discrepancy in the couple simulations are contributing to the circulation underestimations. So we'll conclude by sharing a few takeaway messages. First, prescribed sea surface temperatures models simulate significantly larger southern hemisphere circulation trends than the coupled models. And pacemaker experiments confirm that sea surface temperature trend discrepancies in the tropical Pacific and Southern Ocean are connected to circulation trend underestimation in the coupled models. And as a final piece, I would like to note that reanalysis uncertainty in the Southern Hemisphere circulation is very large. You can find related results and more discussions in our paper under review. And I would like to note that it will have a slightly different title from this talk. And the title is going to be revisiting the reanalysis model discrepancy in the Southern Hemisphere storm tracks. Thank you. And I would like to take any questions.
Great, thank you so much.
Thanks.
It's a really interesting talk. Yeah, let's have a few minutes of questions for Joonsuk, and then we can open the floor to discussing any of the thoughts people had on the talks in this session. I guess while people are warming up, I had a question towards which I was thinking about towards the end was so it seems like yeah, maybe this is a good figure actually. So it looks like does this suggest that the tropics are more, or not this figure particularly, but does these results in general suggest that the tropics are more important for saying this trend than local SSTs? So getting the tropical SSTs right is more important because you have these simulations where you're nudging both of them, and it seemed like you only get this big red blob when you nudge the tropics.
Right. The red blob is important, but when you look at the simulation, when we just nudge the tropical Pacific, it produces some kind of cooling trend, weakening trend outside the South Pacific. So I would say for the South Pacific, the tropical Pacific is important, but it is not enough to get the overall structure of the strengthening trend because it's just impacting this particular region. So if you want to get overall intensification across all other longitudes, we also need local SST trends as well.
Thanks. That clears it up. Jonah, do you want to go next?
Sure. I just had I just had a question about, do you expect that these discrepancies in the circulation could help explain, and forgive me if this is if you're saying this and I wasn't getting it, but if the discrepancies in the circulation could help explain the SST problems in the first place, that if there's some sort of positive feedback between, if you have better reconstruction of the circulation, if that would play a role in giving you the right warming pattern in the Southern Ocean.
Yeah, I think I'm aware of some other works that say that Southern Ocean cooling can be also wind driven. So I think if you strengthen the circulation by Southern Ocean cooling, that will, I think, could bring positive feedback because surface wind will also get stronger. So yeah, I think there is a possibility of this positive feedback there as well.
Yeah, thank you.
Cool. Vince, do you want to unmute yourself and ask your question?
Yeah, sure. Hopefully you can hear me okay. There's a little bit of a background noise, but I was wondering, I expected the reanalysis and AMIP to look quite similar. And I think in one of the earlier slides, they look similar or more similar than the historical free running runs. Yeah, I think you just had the slide up that I was thinking of with the spatial patterns across the Southern Ocean. They look pretty, yeah, kind of like different in where the maximum is, like the AMIP 6 mean versus reanalysis. It looks like the reanalysis has this really strong trend kind of south of Australia, like the peak where it is across the Southern Ocean is different. Do you have any idea why there are differences between the reanalysis and AMIP 6, like what's causing those? Thanks.
Yeah. I have to say that I don't have a clear explanation in terms of whether there is like forced differences. I should say there could be some difference in the internal variability because we also find just from the CSM2 prescribed sea surface temperature simulation, there is a huge spread in the trend. So I think what maybe is causing the difference is that there is internal variability in here, and AMIP 6 mean is kind of smoothing out all the internal variability, whereas the reanalysis mean is just one realization of internal variability.
Okay, that makes sense. And the one follow-up I have is, do you know whether the reanalysis uses the same SSTs as AMIP? I think that some of them have, I'm not sure exactly whether they're the same or not. So just curious about that too.
Yeah. AMIPs, so they don't use the same SST, and in fact, all reanalysis use slightly different SSTs. And yeah, that's something we could also look at, whether the differences in the reanalysis SST data sets can explain some part of the spread in the trends we find. Yeah, that's a good thing to know.
Great, thanks.
Thanks.
That's great. So we've got a few minutes left before the hour. They might be nice to bring back together some general thoughts in the session. There was some discussion going on in the chat which I didn't fully monitor, but did people come to some agreement about what's happening with solar absorption in Jakob's model?
I wouldn't say agreement, but yeah, I think one of the arguments is that it's pretty low. So I just basically Googled it and found it's around 3% of the incoming solar radiation, but it could be more. And then also like solar absorption will be somehow like it's incorporated in these arts calculations. So maybe we somehow incorporate it in the conceptual model, even though we don't formally do so. But yeah, I'm not sure about this. Like I would have to think about it a bit longer, but I think mostly it's because it's pretty small.
I should add that, if I may, shortwave cloud absorption, was a big controversy in the late 90s. And some people have been around at that time may remember that. But it was not necessarily about ice clouds specifically, but there were actually campaigns to try to measure shortwave cloud absorption. If anybody who was around at that era can support me and confirm what I'm saying, but it was a big controversy. But in the end, I think it was decided that we were our understanding of shortwave absorption and fitted the observations we had at that time. anyway, yeah, it's something worth understanding why neglecting it doesn't matter. Thanks.
Cool. Nader, go for it.
I also had a question for Jakob. Guess towards the end of your talk, I realized I wasn't totally sure how you had diagnosed the emissivity and other cloud properties as a function of ice-water path. And it seemed like maybe you were doing it using the model equations, the simplified equations that you'd written down. So then the nice agreement that you showed between the model prediction for the albedos and the simulation data you were using, is some of that agreement built in because you're using the model relationships to diagnose the parameters?
Yeah, I see what you mean. So basically what we did is that we used the Arts radiative fluxes and then rearrange the model equations that we have to diagnose, for example, the emissivity. So for the emissivity, we first diagnose the cloud top temperature based on more or less brightness temperature, and then from if we know the temperature, we can like rearrange the equation that we have for the flux emitted from the high cloud based on our conceptual model and what we have from the Arts simulations to diagnose the emissivity. So in a way, yes, it's like the agreement is somewhat built in, I would say, but if this assumption was totally wrong, then we would see like a weird shape for the emissivity. That doesn't make sense. Yeah.
Yeah, that's fair. Thank you.
And I guess what's neat there is that you don't need all of that scatter around those fits that you have in order to get something that's quantitatively accurate.
Yeah, exactly.
Yeah. Cool.
Right, and if the relationships weren't so physical, you probably see a lot more scatter. And I think for some diagnostics, you saw a considerable amount of scatter and others less.
Yeah.
Yeah. Cool.
Yeah, I think some of the scatter is also just due to the noise in the data, like for example, in the cloud top temperature. But yeah, you're right. Like if it would be completely unphysical, we would see more scatter in the emissivity, for example, some stuff like that.
Great, thank you.
Great, cool. I guess end off with just one quick question for Paulina, which I also had. So with this like square root dependence of methane and things, and so there's talk in the chat about spectral overlap and stuff. I mean, maybe have you thought more abstractly about what would need to happen for there to be a square root dependence? It seems like people are able to get, logarithmic dependencies and linear dependencies. Like, can you construct some like weird molecule or something that would actually have a square root dependence? Is that something or overlap between gases or something?
Yeah, so actually the square root dependence, I think they explicitly do, like, the methane forcing is square root and then they subtract away all the overlap. So I think the IPCC argument is that it would be a square root even if it was just N2O or just methane. I guess my argument would be that a square root looks a lot like some lines and some logs added together. And that's what my physical interpretation of how you would, my interpretation of how you would get to something that is that shape. But I very briefly thought about how you would get a square root and the deriving from the Schwarzschild's equations or from the shape of the spectrum, and I don't have a good idea for that.
Yeah, it seems like there'd have to be some fairly convoluted set of conditions for that to work, right?
Yeah, I guess I guess the argument is that the square root dependence comes from the strong line limit, so you would have to have enough strong lines. But then you also have to have, there's some other assumptions that are made, I think, in the strong line limit, which may not be necessarily not carry through all the way. So short answer is I'm not sure.
It's interesting though.
I mean,
Yeah,
I think if you think an analogy with CO2, the log scaling just comes from the fact that the absorption spectrum is exponential and you end up, and the inverse of that is a log.
yeah,
And that's where the log comes from. So I guess if your absorption fell off, quadratically from the peak, then you would invert that and get a square root. I don't know if there's any molecules for which the absorption falls off quadratically, roughly quadratically from the peak, but I suppose that would give that result. I think Jake Seeley in his
Yeah.
thesis played with, the synthetic spectrum of like a made up gas, gave it some funny shape to see how it would affect the forcing. So anyone who's interested in this kind of a sort of hypothetical can check out the thesis and Jake Seeley's thesis, and there's something about that there.
cool, thanks, so well.
Great. Well, thanks everyone. My laptop's about to die, so we should wrap this up. But yeah, thanks for coming. Let's thank the speakers again for 3 fantastic talks by 3 early career scientists, which is great stuff. Yeah, and see you guys next month. Take care.
Thank you.
All right, thanks.